Let's consider the magnetic levitator system. Here, the objective is to control the top of the ball in this line with respect to the reference line y equal to 0, denoted here in this green dash. This line is obtained when we just place the ball on the base of the setup. In that situation, we count the top of the ball, y equals 0. The ball is being affected by the gravitational force mg, and here we want to generate a counter force Fm to lift it up. And we can do that by changing the current through the coils here. If we just consider the dynamics of the ball, here is governed by the Newton's law. On the left, you see that this is the mass times acceleration equals the total force that contains the force due to the magnetic force subtracted by the gravitational force mg. This equation doesn't look that complicated. What do you think is the main challenge here? The main challenge comes from how we generate the Fm itself. The Fm, or magnetic force, is actually dependent on two variables. That is the amount of current we inject into the coils, and also it depends on the position of the ball. A simplified relationship to describe this is given in equation 2. Substitute this back into equation 1, we will have equation 3. Observe that now we have y on both sides of equations. And because of how y appear in the equation 2, we now have actually equation 3 as a nonlinear dynamical equation. This is not nice because all the linear technique that we learned from the class, for example, Laplace transform, doesn't directly work here. So we are going to make a linear approximation of equation 3 in the form that become convenient for us to apply our control techniques that we have learned. The first step is to consider the behavior of equation 3 around nominal operating condition, that is, around the nominal current value and nominal position value y. Here we see that the current actually is a summation of the nominal values plus some small deviation around it. Also, the position y is a nominal y plus a deviation of y around it. With that in mind, we can write equation 3 in this form, where we denote explicitly the y as the nominal ones plus deviation, also the same to the I. The first order Taylor expansion can be made, particularly on the function Fm. Here on the left side, we still have the same thing. We just distribute m into the brackets, and then denote the time derivative 2 times with double dot. On the right side, the Fm is approximate here with these 3 terms. So with the first order Taylor expansion, you denote Fm at the nominal values plus the deviation due to I and deviation due to y. The term mg just follows directly from the previous one. Observe that with the nominal values of I and y, we have nominal force Fm here. Together with the gravitational force, we describe the nominal acceleration. An example of this is when I star and y star just produce the right force that cancel precisely the gravitational force and make the acceleration of the nominal y is equal to 0. In that case, we can, for example, cancel this part out and consider only the deviation of y due to the deviation of I. With the known values of I star and y star, we obtain a linear differential equation here. We can take the Laplace transform of this to go to the S domain. This is indeed the linear approximation part of the dynamics that we want to design our controller for. Hope that this gives enough hint for you to proceed with the lab assignment.